Okay, so for what we have in the case of quadratic functions, okay, now quadratic functions are going to be second degree functions. Okay, so for what we have in the case of quadratic function, okay, so this is going to be a second order function. You're going to have a second order function whose standard form is going to be y is equal to f of x is equal to ax squared plus bx plus c. And just like in the quadratic formula, okay, we're going to have that a does not equal to 0. Okay, so just kind of stress in case you have a second order function, and we're talking about second order as in second degree in x. And again, so you have this standard form layout, and we're going to get back to this particular form, but there is another presentation for the quadratic function, and this is going to be what is referred to as the vertex form. And for what we have in the case of the vertex form of a quadratic function, okay, so we're going to have y is equal to f of x, and we're going to have the same leading coefficient a, but for the vertex form, again, we have a times the square of the binomial x minus h, and then we have followed by a constant value k. Right? And for the vertex form, okay, now this is, we're looking at the same function. Okay, again, ax squared plus bx plus c is the standard form. Vertex form, you have this other layout, and just some guidelines here. So we're looking at the same coefficient a, and now for the leading coefficient a, if a is positive, then you're going to have the graph of the function and it's going to open up from the vertex. And the vertex is a particular point. And the general coordinates will be h and k. Now, if we have that a is negative, okay, so this is what I've got for a is positive, okay, but almost the same terminology, okay, but in this case, right, so if a is a negative value, okay, so a is going to be less than 0, and you're going to have the graph of f of x to be opening downward from the vertex. Okay, and there's another thing too. Okay, so you got a, okay, so again, if the leading coefficient is positive, the graph is going to open upward. If it is negative, then the graph opens downward. Okay, and now where the variables h and k will come in. Now there is one component, sort of a dividing line. That's going to sort of shape the behavior of the graph of a quadratic function. And this is what we have in the case of the axis of symmetry. Okay, the axis of symmetry, x is equal to h, and this is going to be a visual vertical line. It's not the graph itself, but that's going to divide the graph of f of x into equal mirroring halves. And for what we have in the case of h and k, okay, again, that is going to be the vertex. And as already stated, okay, this is going to be the point from which f of x opens. And just looking at what we have in visual layouts. Okay, and we are once again working with the XY coordinate system. And so we have a point on a vertical line. Let this be the vertex. Okay, so we have h and k. Again, just for the graph of the function, we'll just have the function to open upward from this point. Again, so you have y is equal to f of x is equal to a times the square of x minus h, followed by the sum of k. And again, this is still the same f of x. That is ax squared plus bx plus c. Okay, and for what we have in this particular layout, okay, so we have with the coefficient a, okay, so again, a is positive, And how do I know it's positive? Well, because of the graph, it is opening up from the vertex. In this particular case, all right. And if you notice, you have your bottommost point for the graph at h and k. And so the vertex is going to be regarded as the minimum. And another thing too, okay, if you notice, you have this dividing line, and we have the x is equal to h, and this is going to be the axis of symmetry. All right, so this is a case of where we have the graph to be opening upward. Now let's say that we have another case with quadratic functions. I'm just going to copy this and make some modifications. All right. Very much the same layout, but you have the graph to be going in the other direction. In this particular case, right, so A is going to be negative. Again, we're still looking at y is equal to f of x is equal to the vertex form we have here, as well as the standard form, and this time with A being negative, and we know it's negative because the graph now opens down from the vertex. And we just looked at relative minima and maxima, and for what you have here, okay, the vertex is the relative peak point, so the vertex is going to be regarded as the maximum. Now, looking at what we have as a specific case of what we have with the quadratic function, say we have here given f of x, or y is equal to f of x, is equal to, say we have the quantity of x minus 2 squared plus 5. Say if we were to determine the following, okay, and just looking at what we have in the construct, okay, of this particular vertex form, okay, we can determine the direction that f of x opens, the axis of symmetry, as well as the vertex. Okay, so for what we have here, okay, so we got, again, the general layout of the vertex form. So you have f of x is equal to a times the quantity of x minus h to the second, followed by the addition of k. And for what we have specifically, okay, so we have that f of x is equal to, again, the square of x minus 2 followed by the addition of 5. And now, for what we have in the case of what will represent a, h, and k, all right, so you don't have a explicit coefficient in front of the square of x minus 2. So what you want to have here implicitly, okay, you want to have that a is equal to 1. And we'll go ahead and get the h value. Okay, now your h value, that is going to be the 0 of whatever the independent variable expression is. And we have here, we have the expression to be x minus 2. And if I set this equal to 0, well, if x minus 2 is equal to 0, we have that x is equal to 2. And also, in the case of the k value, well, k is going to be the constant value, which is going to be positive 5. Okay, now for the direction that the graph of f of x opens, okay, now this is contingent upon the sign value of the leading coefficient a. So you got a is equal to 1. So we have that a is positive. And anytime that the leading coefficient is positive, the graph is going to open up. Okay, now for the axis of symmetry, now we had arrived, okay, from having the representation of x minus h with x minus 2 set equal to 0. We have the x is equal to 2. And for the axis of symmetry, now I'm just going to use AOS for short. The axis of symmetry, x equals h, and that's going to translate to x is equal to 2. Okay, and again, for what we have in the case of the vertex, okay, all right, so just again, okay, we had our x value, which is our h value as well. Okay, so you got h is equal to 2. We have also that k is equal to 5. So for the vertex hk, we have with the specific coordinates, okay, which will be 2, 5. Okay, so just looking at what we have with this first case. All right, so again, we have our quadratic function in vertex form. A is positive, graph opens upward. X minus h is going to have h to be the 0 of our variable expression in x. Okay, so x minus 2 is 0. X, thus h, is equal to 2. So the axis of symmetry, we have at x equal to 2. And with the k value at 5, and recycling the h value, which is the x value 2, okay, we had the vertex to be situated at 2, 5. And just looking at what we have, so we got Okay, so if you notice, we have f of x is equal to the square of x minus 2, followed by the addition of 5. And now for the graph, okay, that is going to be in red, okay, and this is opening up from the vertex, okay, which we have at 2, 5. Okay, so this is going to be the minimum of this function. And again, for this line that is in blue, okay, again, this is dividing up the graph of the parabola, representing what we have for the quadratic function into equal mirroring halves. Okay, so for this dividing line, again, this is going to be the axis of symmetry, which we have at x is equal to 2. Now, another case, and let's say that if I change the function, okay, and say if I go from this function to where I have that f of x is equal to just 3 times the square of x minus 7. Okay, so we got with this vertex form, again, so in the general layout, for the vertex form, we have a times the quantity of x minus h raised to the second, followed by k, and we have that in the given function. Okay, so you have f of x. Again, we have the explicit coefficient at the front, given at 3. So we have for the value a, okay, you have the leading coefficient. So that is at 3. And again, we have that 3 is a positive value. And once again, we're going to have the graph of this function to open upward. And looking for the h and the k values. Okay, so you got for this situation, okay, if I set x minus 7 equal to 0, so we have that x is equal to 7. Again, that which represents h is going to be the 0, which you have with x equal to 7. So you have x is equal to h is equal to 7. And we have with the axis of symmetry, we have the x is equal to 7. And if you notice, okay, we have a void among the terms, okay, so we have just plain 3 times, okay, the square of x minus 7. Nothing is added or subtracted past what we have with 3 times the square of x minus 7. Okay, so if there's nothing added or subtracted, we're going to have that k is equal to 0. And so we have with h at 7 and k at 0, it's going to follow that the vertex is going to be 7, 0. And for what we have, okay, for the graph of this particular quadratic function, okay, so I have 3 times the square of x minus 7. And again, we have the axis of symmetry. Okay, this time we have the vertical line. We have the x is equal to 7. And again, we have the vertex located at 7, 0. And again, for the graph of f of x, you have a parabola, okay, that is going to be opening upward. All right. And now, just looking at expanding the model a bit, okay, which we will get to in a moment. Okay, so we got, let's say that if I were to change directions, now let's say if I have f of x equal to -4 times the square of x plus 1 minus 5. Now to determine, okay, all of these same components once again. Okay, so you got f of x again equal to -4 times the square of x plus 1 minus 5. Okay, so you want to have that a is equal to -4. And with a is a negative, this means that the graph is going to be opening downward. And if looking for the h value, okay, this time we're looking at setting x plus 1 equal to 0. And if x plus 1 is 0, you have the x is equal to -1. So you have, again, your h value and x value are the same. Now for the axis of symmetry, okay, so we're going to have x is equal to -1. And for the k value, notice we have the subtraction of 5 at the end. So you have that k is equal to -5. Okay, and so we got h is equal to -1, k is equal to -5. And for the vertex, hk, again, h is -1, k is at -5. And so we have -1, -5. Okay, and so for what we have in this particular layout, okay, so you got the graph of y is equal to f of x is equal to -4 times the square of x plus 1, followed by the subtraction of 5. And the graph is opening downward. And again, we have for the axis of symmetry, again, we had that the axis of symmetry is that x is equal to -1, and the axis of symmetry always runs through the vertex. Again, the vertex we have situated at -1, -5, and that is going to be the relative maximum. And again, for the rest of the activity, okay, you have the remaining points, okay, to be beneath. So the parabola is opening downward from -1, -5. All right, now looking into further details. And let's say if we have a quadratic function, and we'll look for more than just 3 items here. Let's say we have given f of x is equal to the square of x plus 4 minus 4 and we were to determine the following. Okay, so you're still looking at the direction that f of x opens Second, once again, the axis of symmetry. And then we have the vertex. And for what we have in addition, okay, the x and y intercepts. And say at least 5 points. And that's including the vertex and the intercepts. Okay, so we have this function provided in vertex form. And once again, for the first 3 parts, okay, we can determine, okay, just what, okay, the direction will be, the axis of symmetry, as well as the vertex. And so just looking at what we have now. Okay, and let me plug this in. Here we go. All right. Okay, so again, we have, okay, looking for A, H, and K. So A, again, that's going to be implicitly at 1. So you have A is equal to 1. A is positive. So we're going to have the f of x is going to open upward. Now for the determination of the h and k values, okay, so this time we have x minus h to be represented by x plus 4. And if I set x plus 4 equal to 0, so I have x is equal to -4. And again, that x value and h value will be one and the same. And so we're going to have for the axis of symmetry, Okay, so you have that x is equal to -4. Again, we have with the k value, okay, so that's going to be at -4. Alright, so we got h is equal to -4, k is equal to -4, and for the vertex, okay, with h and k, so we're going to have -4, -4. Now, for what we have after the first three portions, now for the intercepts, again, we're looking at x and y intercepts where they exist. Okay, now again, just for the quadratic function, again, f of x is another way of saying y. And we have y is equal to the square of x plus 4 minus 4. And if we look for the x-intercepts, again, the general coordinates of the x-intercepts will be where we are looking at solving for x as y is set to 0. So, setting to 0, what we have for y. Okay, so we have that 0 is equal to the square of x plus 4 minus 4. And there are various ways you could solve for x. You could square out x plus 4 and set up a quadratic equation in standard form. And you could also isolate the square of x plus 4 and use the square root property of equality. And we'll go that route. Okay, so if I were to add 4 to both sides, we have that 4 again is equal to the square of x plus 4, and what I'll do here is just switch sides. So we have the square of x plus 4 equal to 4, and again along the lines of the square root property of equality. So if I have the square of an expression set equal to a constant, and say that expression is equal to plus or minus the square root of the constant. Okay, so the expression, we have an x plus 4, so going from just the square of x plus 4 to x plus 4. Okay, so I have x plus 4 is equal to plus or minus the square root of 4. And the square root of 4 is 2, so there'll be two destinations for x. One is going to be where we have x plus 4 equal to -2, and where we have x plus 4 is equal to 2, and getting these x terms by themselves. Okay, so if we subtract 4 from both sides in both equations, okay, so if x plus 4 is -2, x is going to be -2 minus 4, which will be -6. And if x plus 4 is equal to 2, well, x is 2 minus 4, which will be -2. So we're going to end up with a couple of x-intercepts. And we can say that we have x equals -6 as well as x is equal to -2. And you can also write this in coordinate fashion. We have -6, 0, as well as -2, 0. And for what we have in the case of the y-intercept, okay, so we're taking turns along the lines of, okay, what to set to 0 and what variable to solve for. So here we're solving for y. Okay, so we have that y is equal to f of 0 and replacing x with 0, so you have 0 plus 4 squared minus 4, and 0 plus 4 is 4, and so we'll have 4 squared minus 4, and 4 squared is 16, and 16 minus 4 is equal to 12. Okay, so we'll have one y-intercept, and that's at y is equal to 12. Again, this can be expressed in ordered pair terms with 0, 12. Again, with the x-intercepts, we have y at 0, and with y-intercepts, it is x, which is set to 0. All right, so you've got 3 intercepts altogether. And just looking at what we have for the points that will make up the graph of this particular function. Okay, so just looking at the mechanics throughout, so f of x opens up, and the axis of symmetry we have at x is equal to -4, and just zooming in. Okay, so you got the axis of symmetry. We have x equal to -4. Again, the parabola is opening upward. Again, it's referencing the square of x plus 4 minus 4. And we have with our points, so we got the vertex, and we have the x-intercepts at -2, 0 and -6, 0. Again, the axis of symmetry. Okay, again, we have x equal to -4, and if you notice, okay, we have the y-intercept at 0, 12. Okay, so just looking at what we have right now, we got 1, 2, 3, 4 points right now, and what you can do, okay, is that you can, okay, now this parabola has an infinite number of points, but we can kind of use the y-intercept to determine what, let's say, fifth point there is without having to do any calculations. Okay, if you notice, okay, we have the axis of symmetry. Okay, we have at x is equal to -4. Okay, so like point here, we got -4, 0. And if you notice, okay, immediately to the left and to the right, okay, we have -2, 0. So you have 2 spaces to the right. -6, 0 is going to be 2 spaces to the left. And say if I were to move up the axis of symmetry level with the y-intercept, so here I would have -4, 12. And going from, say, -4, 12, okay, which is level to the y-intercept, so I'd be shifting over 4 places to the right. And if I were to attain, let the fifth point be that which is level with the y-intercept, so I can go 4 spaces to the left. So you got like going from x equals 4 to x equals 0, and then shifting over 4 units. And say that I have a fifth point, which is going to be -4, 12. Okay. And there are other ones too. Okay, kind of like it could supply other points, like here. Let's see, 3 spaces to the right. This would be like -1, 5, and 3 spaces to the left of x equals -4. So that would be, in this case, that would be -7, +5. So those would be additional points that would make up the graph of this particular quadratic function. All right, and now just looking at what we have now, looking at quadratic functions. And this time around, let's see what we get for, let's say we have that f of x is equal to, and we'll say that we have so you have -2 times the square of x minus 3 and we'll add to this plus 18. Okay, let's see what we get for these components here. The direction that f of x opens, the axis of symmetry, the vertex, as well as the intercepts, and at least 5 points on the graph of this function, given f of x equals -2 times the square of x minus 3 plus 18. And we'll discuss in the next few minutes. Okay, if you're still working on these, that's fine. Again, we have this function to also be laid out in vertex form. Okay, and so for what we have here, identifying a, h, and k. All right, so we have a is equal to -2, and since the leading coefficient is negative, okay, we're going to have that the graph is going to open downward. And for the h and the k values, okay, so h is going to be the 0 of x minus 3. All right, so x minus 3 is equal to 0, so we have that x is going to be 3, which is, again, the h value. And for the axis of symmetry, again, that is going to be x is equal to 3. And we have for the k value, so that k is equal to 18. Okay, all right. So we already have lined up. Okay, h is equal to 3, and k is equal to 18. And so for the vertex, this will come out to 318. Okay. Now regarding, once again, the intercepts. Okay, once again, for the x-intercepts, okay, you're setting y to 0 while solving for x. Okay, So you got y is equal to 0. Okay, and we have is equal to -2 times the square of x minus 3 plus 18. And I can isolate the variable expression. Okay, so I can take 18 away from both sides. So we have that -18 is equal to -2 times the square of x minus 3. And we have dividing by -2. Okay, so -18 divided by -2 is positive 9. And we have that 9 is equal to the square of x minus 3. Now I'll just switch the sides. So I have the square of x minus 3 is equal to 9. And again, reapplying the square root property of equality. So we have x minus 3 is equal to plus or minus the square root of 9. Okay, so we got x minus 3 is equal to plus or minus 3. Okay, and so for what we will have specifically for x will be two distinct values, one of which will be attained from setting x minus 3 to -3, and the other x minus 3 equal to positive 3. Okay, so looking at solving for x. So if I add 3 throughout, okay, so for the first equation, x is going to be -3 plus 3, which will be 0. And for x minus 3 equal to 3, we're going to have that x is equal to 6. So we have two distinct x-intercepts. We see we have x is equal to 0 as well as x equal to 6. Or as ordered pairs, we're going to have the origin as well as 6, 0. And for the y-intercept, okay, there's going to be a repeat in a sense. Okay, and we're going to have that y is equal to f of 0. And it's equal to -2. Now again, x is set to 0. So you got y is equal to -2. Now 0 minus 3 is -3. So that is going to be squared. And the square of -3 is going to be 9. So we now have -2 times 9. Followed by the addition of 18. -2 times 9 is -18. And -18 plus 18 is 0. And for the y-intercept, okay, so you have y is equal to 0, or once again we're going to have the origin, and the origin has the distinction being that point, the only point that can be in the real number system, an x-intercept as well as a y-intercept at the same time. Okay, and so we have, in the case of the layout, There we go. All right. So we have with this quadratic function, again, the graph is opening downward. And we identified the vertex at 318. Again, the axis of symmetry, okay, we have x is equal to 3. Okay, so we got the vertex at 318. And again, we had the y-intercept at 0, 0, which is also an x-intercept. And the other x-intercept we have at 6, 0. And I just want to mention, okay, for other points, okay, say if you were to go down the axis of symmetry, x is equal to 3, okay, and we have, say, just lining up. So if I go one place to the left and one place to the right of the axis of symmetry and land on the graph of the quadratic function, okay, we have, again, one place to the left, one place to the right. So I have 216, 416. If I have two places to the left and also two places to the right, same y value, I have 110 as well as 510, and then just descending to the level of the x-axis, so I got 3 places to the left, 3 places to the right, where we have the origin as well as 6, 0. So with this approach, I got 1, 2, 3, 4, 7 points in this case. All right, now looking at what we have alternating between vertex and standard forms. And for what we have in this particular layout, okay. Okay, so for what we have in the case of converting from standard to vertex form, I'll just give you one particular exercise. Again, you had the standard form, whereupon we had that y is equal to f of x is equal to ax squared plus bx plus c, whereupon a does not equal to 0, and we have for the vertex form once again, we have y is equal to f of x is equal to a times the square of x minus h, followed by the addition of k, and let's say that we have let's say we have f of x is equal to, let's say we have x squared plus 6x plus 8 to vertex form, and then determine the vertex. Okay, so we have for this setup here, okay, so you have f of x is equal to x squared plus 6x plus 8. Okay, so again, this is the standard form. Okay, now in terms of converting to the vertex form, now next portions, operations, have maybe a little bit of a feel of factoring by grouping, but we're not doing that by any stretch of the means. Okay, so if I were to separate the variable terms apart from the constant, and that is just put x squared plus 6x and just set apart from 8. So got parentheses around x squared plus 6x, and then we have for the next part, and this is going to be what's referred to as completing the square. Okay, and what I mean by this, I'm going to get like the variable expression into that, which will be a binomial times itself. Now, x squared plus 6x plus 8. Okay, that is a trinomial that is factorable, but that would have factored out to x plus 4 and x plus 2. And I'm trying to get a variable expression that would factor out to like x plus something times itself. Okay, so we have at this stage, okay, so we got what f of x equal to x squared plus 6x followed by the addition of 8. Now where the completion of the square comes in, so in the parentheses I want the first term to have just the variable to the second, no coefficient other than 1 in front of it. Okay, so we just x squared at the front. I'm going to take the first order term coefficient. Okay, first order term is 6x. I'm going to take the coefficient, which is 6, and for completing the square, whatever is in front of x, I'm going to take half of that and square. So half of 6 will be 3. In turn, 3 squared, or 3 times 3, is equal to 9. And I'm going to use this 9 to add to x squared plus 6x. Okay, so right now we have f of x is equal to x squared plus 6x. I have plus 9. And so I have the plus 8 to follow. Now I have to create a little bit of a balancing act because I need to offset the surplus that is created at the front. If you notice, x squared plus 6x is followed by 9 and then plus 8. If I add 9 and 8 together, and we'll have 17, but I want to get it back to the addition of 8. So to undo the excess created by adding 9, I'm going to subtract 9 at the back. Okay, so just get it back to square root 1 with x squared plus 6x plus 8. So we have now, we got f of x is equal to x squared plus 6x plus 9. And 8 minus 9, okay, that is going to be at negative 1. Now with x squared plus 6x plus 9, okay, if I were to factor, okay, it would turn out that x squared is going to be the square of x, and 9 is going to be the perfect square of 3. And think of it like this, x plus 3 times itself, you got x squared, and you got 3x plus 3x is 6x, and 3 times itself is 9. And guess what? How I got to 9 in the first place originated from squaring out positive 3. So for what we have in this case, right, so we come out to, let me change that back. Okay, so we have the square of x plus 3, okay, followed by the subtraction of 1. All right, so we have for f of x, we have the square of x plus 3 minus 1. Okay, so this is going to be the vertex form. Okay, and just yes.
Can you explain again why you subtracted the 9?
Okay.
Why do you have to do that?
Okay. Think of it like a balancing act. Think of like the scales of justice. Okay, you got to keep things in balance. Okay, so when I complete the square adding 9, remember if I didn't do that, I would have x squared plus 6x plus 17. But I wanted to keep it in line with x squared plus 6x plus 8. If I did not add the 9, if I did not take away the 9, I would have x squared plus 6x plus 9 plus 8, which would be 17. But I want to get it back down to x squared plus 6x plus 8. So to undo the surplus created at the front, I'm going to take away the same amount. So I'm back to x squared plus 6x plus 8.
Okay.
Yeah. And what I'm trying to do, the reason I'm keeping that 9 is that I'm trying to convert to the vertex form. So I need the variable expression to be the square of something. And I need that 9 to form that trinomial. I need that 9 at the front. So think of it like this. Okay, notice I have x squared plus 6x plus 9, and I took 9 away from 8. Okay, and guess what? If I were to go back to the standard form, I have like x squared plus 6x plus 9, and if I take away 1, I'm back to x squared plus 6x plus 8, or standard form. But I'm writing this trinomial in terms of the square of a binomial expression, which is going to be the square of x plus 3. And then I have the minus 1 to follow. Okay, so for what we have at the front, okay, so you have implicitly, okay, so I have that a is equal to 1. And for the h value, okay, remember, if x plus 3 is equal to 0, so you have x is equal to negative 3, and that's going to be your h value as well. And for what we have in terms of the k value, again, so we have that k is equal to negative 1. Okay, so you got h is equal to negative 3, and k is equal to negative 1. And so it's going to follow that for the vertex. Okay, we'll have the ordered pair, which is going to be negative 3, negative 1.